Okay, so I think it's oh, all right, quiet down, please. So I think it's fair to say we're in the home stretch here, and let me just see if I can get this down a little bit here. News item today isn't exactly sort of a big headline, but I thought it is relevant to today's lecture. This is, maybe you've seen this kind of thing before, but it's a new interface. So the topic for today's lecture is input-output, and so I thought this was kind of fun to look at. This is a new system that came out of, I think, Microsoft Research and Carnegie Mellon, where basically what you get is a little projector and a camera, something similar to the Kinect camera, and you can basically project a touch screen anywhere. So, you know, there's this great little demo of being able to use your hand as a keypad to make a phone call, or this one here is, you know, you're projecting a map, and you can then stretch it using, you know, multi-touch types of gestures. So it's just kind of a good. This started off, I'll talk a little bit about it when we get there, but there was kind of a demo or a thought experiment that the MIT Media Lab did, and all of a sudden it looks like now it's going to be commercialized not that much later. So just a different way to think about how you might interact with the computer, and also a way for us to just talk about how you know, input-output changes what you can do with the computer. And you're not allowed to bring this to the final, by the way, if you get one. Although maybe if you had one, we'd let you use it. I'd try to use it. All right. So, hold on a second. All right, let's try that. All right, so the topic today is I/O basics. But I've got actually a little business I wanted to do, just finishing up on the virtual memory stuff, and then I'm going to launch into the I/O topic. So remember where we left off last time? We had, well, I think last time we killed Dan's laptop, and the way we did that was by understanding how virtual memory works and basically breaking that abstraction that you have infinite memory by basically saying, well, let's see if we have infinite memory, and finding out that, well, maybe we really didn't. But the basic ideas there were that we're going to use memory as a cache for the disk. Although what I'm going to talk about next is that for performance reasons, you don't want to do that too much. And Dan breaking his laptop was a good way to demonstrate that. But what you do want to do for sure is this idea of protection, right? So that you can have multiple processes sharing the same hardware, and be sure that they're not going to interfere with each other, at least by writing on each other's memory. And the other thing we talked about was sort of all the mapping that has to happen. So we talked about page tables, you know, how you map from virtual addresses to physical addresses. And then we talked about this thing called the TLB, the translation look-aside buffer, that's meant to speed up those translations, okay? Which is basically a cache of the page table. So we had, you know, caches for data, and we had caches for instructions, and we have caches for caching address mappings, okay? And the whole reason that this virtual memory abstraction works is this idea of locality. And if you look in your notes, it says spatial locality, but actually it's both temporal and spatial, and maybe even temporal is more important. But the idea is that there's some portion of the memory, it's called a working set, which is the stuff that your program needs for a given point of time. And as long as that fits in physical memory, you know, you're going to get decent performance out of your virtual memory system. All right, so what I want to do now, just to finish up this topic, is talk a little bit more about the performance impacts of this mapping and TLBs. Yeah, in the back.
Is the field entirely separate from the actual page table, like a smaller version of it that's faster?
Yeah, so the TLB is actually a hardware cache that's separate from our other hardware caches that's used for the page table. So just like we had L1 cache.
Is there a page table and a TLB, or do those things?
No, they're different. The page table is stored in memory, and the TLB is a cache of that memory. Okay? So it's important to understand that, and we're going to, yeah. Okay. All right. So, you know, all I wanted to finish up here on this was, you know, this idea that, you know, virtual memory is this beautiful abstraction, but, you know, as an abstraction, it's hiding details of the hardware from the programmer, and, you know, it's, if things aren't set up so that that abstraction can be used efficiently, you can end up with really bad performance. And in general, if you need to access much more stuff than fits in physical memory, then you end up doing what happened to Dan's laptop last time, which is called thrashing, which is basically you spend all your time, you know, looking up an address, finding out that the page that address references isn't in the physical memory, going out to the disk, bringing it in, you know, forcing out other pages and so on. You spend all your time moving things out between the swap space and your physical memory and back, and you don't get any real work done. And that's called thrashing. And so really, if you have a system that's thrashing, you really only have two choices. One is, it sounds facetious, but it's true, you can go out and buy more memory. Okay, the other thing you could do is you know, reduce the problem that you're working on. So, you know, if you have parallelism, instead of splitting into big partitions and then, you know, trying to run each of those big partitions on a separate machine, maybe make smaller partitions and use more machines. Okay, but you want to get to the point where you're actually doing work. You're not just doing swaps between disk and memory. Okay, but we are going to use virtual memory for this idea of translation and protection. So protection we already talked about, which is, you know, we can have multiple processes that think they own an entire address space, okay, and they won't step on each other. It's going to turn out that there's also some memory that only the operating system gets to access. And so that's another form of protection. And then translation is this flexibility of being able to bring in pieces of a virtual address space and put them anywhere in physical memory. And that gives us a lot more flexibility. Okay, and so that's why we need that translation from virtual addresses to the physical address. So, you know, you do get to have processes that are bigger than fit in physical memory, but, you know, if you take advantage of that in the wrong way, you're going to get bad performance. So you got to make sure you have enough physical memory to really run efficiently. But for sure, these benefits of translation and protection are really important. That's what's going to let us run lots of things, lots of different processes concurrently on the same machine. Okay, so let's drill down on performance just a little bit, just to show you how bad this could be. So here's some parameters. We've got an L1 cache, and remember we always want to access the L1 cache in one clock cycle because we need to do that, you know, in every step of our processing. And let's assume we can get a 95% hit rate. So 5% of the time, what we're looking for isn't in L1, we've got to go to L2. When you go to L2, that's a little further away, right? So that's 10 cycles, and let's say, you know, we have a 60% hit rate. So 40% of the time we miss there. Okay, when you miss an L2, let's assume we don't have an L3. So when you miss an L2, you're going to go to memory. Okay, DRAM is quite a bit further away. That's going to cost us 200 clock cycles. So, you know, 1 if it's an L1, 10 if it's an L2, 200 if it's in memory. The problem is, because we're using virtual memory, the address we're looking for might not actually be in physical memory. It might actually be living out on disk somewhere, right, in a swap space somewhere. And in the case where you have to go to disk, that's like, as Dan's been saying, going to Jupiter. But if you remember, actually, those of you who are paying attention, when we brought that up, it was actually going to Pluto, Dan. But Jupiter, Pluto, it's all the same among friends. What's a couple light years among friends, right? So, yeah. But anyway, it's really far away. Let's call that 20 million clock cycles. Okay, so, and that's only 10 milliseconds, right? That's not that long. Okay, but it's a lot longer than the way the CPU is working. So, remember we did this when we talked about caching. We had this calculation. We did average memory access time. Let's assume we don't have to go to the disk. Okay, so we're only going to worry about L1, L2 in memory. So if we have these parameters and we don't have to go to the disk, then we pay 1 cycle to go to L1. 5% of the time, we have to pay 10 cycles to find what we want in L2. And then 40% of those times, what we want isn't in L2, and then we've got to go to memory, and that costs us 200 clock cycles. So if you do that calculation, you end up with your average memory access time is 5.5 cycles, okay? Which is kind of a bummer because we would like to run things faster than that, but that's what you get, okay? Okay, so now let's do the calculation. Now that's just going to Sacramento or wherever we're going. Okay, now let's bring in the fact that we might have to go to Pluto. Okay, so how much is it going to cost? How much is it going to cost if we go to memory that 5% of the time, then 40% of those times, and then there's some portion of the time that when we go there, what we're looking for isn't there. Okay, so how long is that going to take? So it's basically going to be 5.5 clock cycles plus what? Okay, well, it's going to be plus this. 5% of the time times 40% of the time times 1 minus our hit rate in memory. Okay, so if we have so this is basically our memory miss rate. So there's some percentage of the time that when we look in memory, what we're looking for isn't really there. Okay, so we do a lookup in the virtual page table, and guess what? The page we're looking for hasn't been mapped into physical memory. That's a miss, so 1 minus the memory hit. And for each one of those, we're paying 20 million instructions. Okay, so let's say we did a really good job of managing our cache. And you'll find out this maybe isn't such a really good job. So let's plug in 99% there as our memory hit rate. So 99% of the time when we look in memory, what we want is actually sitting in the physical memory. That's good. 1% of the time, we got to go to Pluto. Okay, what's that going to do to our AMAT? Yeah, it's going to raise it just a little bit from 5 to 4,000. Okay, so all of a sudden, with a 1% hit rate in physical memory, we're running 728 times slower than we were running if everything fit in memory. Okay, this is why you don't want to you don't want to get too many page faults. Okay, so if you think about it, if you had a program that took 10 seconds, and let's say it was all memory bound, right? Let's say it was just doing memory accesses. If that took 10 seconds with everything fitting in memory, it would take 2 hours with a 1% hit rate in your physical memory. Okay, so that's really bad. All right, so you want to make sure you can get a decent hit rate. So what happens if you go to 99.9%? Well, we're going to carve off a 0. So, now we're only 8 times or 80 times slower. Okay? So, think about it. This first one out of every 20,000 memory accesses at the CPU has to go to disk, and we slow down from 10 seconds to 2 hours. If we can get a better memory hit rate, right, which we're going to do either we're going to do, let's say, by buying more memory, or maybe we'll be a little more careful about what programs we run, or maybe we'll do a little better job of managing what's in memory. You still get fairly expensive access. And if you really wanted to get things down to kind of what they were before, look at that hit rate you have to have in memory. Okay? So, the moral of the story here is virtual memory, good for protection, good for translation, good for sort of, getting a program started when it's not currently in memory, but once you're up and running, you really want to be running things that are in physical memory as much as you can. Okay, and if you don't, you'll see the performance. Okay, and so any questions about that? All right, so that was all about virtual memory. That assumed that doing our address translation was free, but it's not, right? Because as was just asked, there's this funny setup we have where we have a cache for the page table. That cache is called the translation look-aside buffer. Okay? So what's the impact of the TLB? All right, well, when you do your address translation, you really, really hope that the translation you need is already in that TLB, because if it is, that's going to be fast, right? And you want to do that. It needs to be, about the same speed as an L1 cache miss, and it's kind of the same hardware. Okay? So, if you miss in the TLB and you have to go to the page table, that's going to cost you the same as like an L1 cache misses. Now, these virtual memory pages are not huge. They're bigger than cache blocks, but they're not huge. And so, 4K or 8K, all right? And a TLB isn't usually that big. Maybe it's got 128 entries, okay? So if you think about it, how big a virtual space can you access without missing in the TLB? And in the best case, it's, say, well, maybe not the best case, but 128 times 4K, that's half a megabyte, okay? Now, you can't run very little. If you look on your machines right now and you look at the processes, you got nothing that's taken only half a megabyte, right? All those processes are bigger than that. Even if it's just, this little thing here that's sitting there doing nothing, that's taken more than half a megabyte. So, it's very easy to get into trouble with your TLB as well. Was there a question here? Yeah. How can the TLB be fully associative? I forget, what did we say the TLB was? It was going to be set associative, right? Yeah. Let's say it's not fully associative. But yeah. There's actually hardware. You can build TLBs out of this kind of hardware called, what's it called? Anyway, there are special lookup, there is hardware that's meant for doing associative memory, it's called. And you can have associative memories that basically do in hardware make it fully associative, but we didn't really talk about those. So. But you can get special TLB hardware that makes it doable. Okay, I don't think the MIPS uses it. Okay, so this is a problem, right? So, what can you do to have better performance? All right. Okay, well, there's a couple things you can do. Well, remember the TLB is a cache. It's a hardware cache, just like an L1 cache is a hardware cache. So how did we make our memory caching system run better? Well, we went from having just an L1 cache to having a bigger L2 cache behind it. So you look in L1 first. If it's not there, that's a miss in L1, and you look in L2. Okay, so you can do the same thing with the TLB, and a lot of modern processors now have multiple levels of TLB. All right, not usually more than two, but a lot of processors will have 2 levels of TLB. Okay, so that's one way to speed it up, and you already know how to do that because you understand caching. The other thing is kind of an interesting trick is, remember when we did that calculation, we said, okay, our TLB can have 128 entries, and each entry references 4 kilobytes. What if the entries reference something bigger than that? Okay, so what if the objects that you were reading into memory were things like big images, right, or pieces of video or something like that? You could afford to have pages that were much bigger than 4K, right, because you're going to have to read the whole thing anyway. So a lot of systems support what's called super pages, and super pages can be quite large, not kilobytes, but megabytes. Okay, so the Intel x86, for example, has either regular size virtual memory pages or super pages that are multiple megabytes. The MIPS architecture, I believe, I don't know about the MIPS. Well, let's see. But that's the other thing you can do. So you have the same number of entries, but the things that the entries reference are much bigger. Okay? So that can work. All right. The problem is, how do you tell the system when it should use a large page or a small page? So like I said, for something like an image, using these multi-megabyte pages is a good idea. If what you're doing is storing, small records like maybe addresses, or something like that, then using multiple megabytes per page is not a good idea because you'll get a lot of internal fragmentation. You'll waste a lot of space. So there are different ways to do it. So systems like Linux actually have libraries that you can call that tell the system, hey, for this region of memory, use these large pages. Okay. Mac OS is interesting. It decides on its own whether it's going to decide whether it's going to use these super pages or regular pages. Okay? But the whole idea is to have more hits in the TLB. Yeah. Go ahead.
If most of your processors have more than half a megabyte of memory, why is the page size so small?
If most of the processes have half a megabyte, have more than half a megabyte of memory. Why are the page sizes so small? It's a good question. Because you'll see when we start talking about I/O that on a page fault you have to bring a whole page into memory. Okay, so the question is, it's going to be cheaper to bring if you have a big piece of memory that you're going to use, it's cheaper if you can bring it in one access. But the problem is if you're only using a small amount of memory for like a particular load word or a store word, you'll end up trying to move these huge chunks into the physical memory and back out, and then you're wasting a lot of space and you're wasting a lot of time moving those back and forth between the disks. So 4K was intended to be a size that was reasonable, that you'd likely have some spatial locality in that page. As the page gets bigger, you're likely to use less of it, unless you know something about your application. So that's why that decision's made. But that's a really good question. Okay, one other thing that's worth mentioning, when we introduced the idea of TLBs, and we said, hey, TLB is just a cache for the page table. Why is it called a TLB as opposed to a page table cache? Turns out there is a reason. And the reason is that a lot of hardware actually is optimistic. And what it does is it starts translating the virtual address before it hears from the TLB. So it actually, as it's translating the virtual address, it's looking up the entry in the TLB at the same time. Because a lot of times you map a whole page in, and then once that page is mapped, you start going through it. So the first time you get a TLB miss, and then you go through a bunch of addresses that are all for that same virtual page, which ends up being the same physical page, which is you already know what physical page it is. So you end up in some hardware looking at the TLB at the same time you're doing the address translation. If the TLB comes back and tells you that the address translation you're doing is wrong, then you basically stop that instruction, do the TLB stuff, and then restart the instruction. So that's why it's called a TLB, because you actually can look at it in parallel and then optimistically be going after the address you think you're going after. So that's a little fun fact to know and tell. That's kind of what's happening here. We have a virtual page number. We're translating that into a physical page number. The other thing we're doing, remember, is we're looking at protection. So we want to make sure, do I have the ability to access this page at all? So if I'm running user code versus operating system code, like I said, there are some parts of the memory that are reserved only for the operating system. So you're not allowed to do anything with, if you're a user program, you're not allowed to touch directly the operating system memory. So that's, you can get a violation on user versus kernel. And then as we already talked about, you can get a violation on read versus write. Okay, so if you're trying to write some memory but you only have read access to it, for example, the code segment, it's not going to let you do that. Okay, and in those cases, typically you'll get an exception. And that's what we're going to talk about next time, is how exceptions and interrupts are handled. Okay? But the idea is you want this translation to go fast, and so you want efficient use of the TLB. You want to use these super pages if that's a good thing to do, so that you can basically map. You can have a bigger reach of the TLB. You can map more bytes with the same number of entries. And then if you have to, you'll have to have a multi-level TLB. All right? All right, so I do want to do a clicker question, so why don't we do that, and then we're going to move to a new topic. And I've got Dan here to help me if I mess this up. So, 3 questions. All of them are true or false. The first one, so you got to read the top. It's important. Program's going to try to load a word X, and that load word causes a TLB miss, but not a page fault. Okay? So you miss the TLB, but there's no page fault. Okay, and then true or false. TLB miss means that should I start this thing? Let me start it. See if this really works. Okay, so TLB miss means that the page table does not contain a valid mapping for the virtual page corresponding to the address X, right? Make sure you read carefully. 2 is that there's no need to look up in the page table because there's no page fault, right? Because we told you there's no page fault. And 3 is the word that the program is trying to load is present in physical memory. And it's true or false for all of us. Oh, and then I have to move this thing, don't I? Sorry. Rookie mistake. Okay, and let's let it run for a while. All right, so, like there are enough people in the room that are pretty comfortable with this, so talk to your neighbors, and then we'll start it up again. Hey, Dan? Okay. Oh. All right. All right, and then now that you've had a little time to discuss, we've got a bonus question, too, so why don't you get this one clicked in? We'll get up to about 150. All right, so there's 28 of you that need to click in here. Let's see if we can get it a little closer. All right, so why don't we stop that? Okay, so let's finish up this question, and then we'll see what we got here. So, okay, TLB means that the page table does not contain a valid mapping for the virtual page corresponding to address X. So you've got a virtual address, you look it up in the TLB, but it ain't there. Does that mean that you don't have a mapping, a valid mapping for that thing? Right, that is false. Because remember, the TLB is tiny, tiny, tiny. Memory's big, big, big. And there's a lot of stuff mapped into memory that doesn't show up in the TLB. Okay, so that's that one. There's no need to look up in the page table because there's no page fault. I don't even know what that one means. That's false. That's false by definition. Okay, and the word that the program is trying to load is present in physical memory. Yes, because we said there's no page fault. That means what you're looking for was in physical memory. Okay, so that was there. Now we've got another question that might be a little more personal. All right, so let's see, how'd we do? You guys are awesome, not bad. Interestingly, talking to each other had virtually no effect on that distribution, so clearly we have some very strong-willed and strong-minded people here. And that's not a bad thing, although being strong-minded and wrong is not always a good thing. Almost right. Dan said, I really assume they were the same person, and they might not be. Okay, so let's do one more. What do I do here? Oh, okay, so help me out here, Dan. Do I have to go question 2? What do I do? Oh, I see. Ah, there it is. Okay. Now this one, Dan very cleverly forgot to ask you so that I get the blame. But here's the question. Project 3, who remembers Project 3? Okay, good. And this is really to help us. Oh. Okay, so how much time did you spend, this is in hours, not days. How much time in hours did you spend on the project 0 to 8? If so, if you spend 0 to 8, please see me after class. I have a job for you. 8 to 16, 16 to 32, 32 to 64, greater than 64. Okay, up. All right.
Mr. Franklin,
Yo.
is that personally or as a team?
I don't know. What are we after here? That is a good question. Yeah, I think.
Team hours and then divide by 2?
Yeah, well.
Or divide by team size?
Yeah, team. Yeah, I guess so. How many hours did you personally spend on it? And this doesn't include having nightmares. And this doesn't include complaining on Piazza. That you do on your own time. All right. So, they may have been a little bit of we get the basic trends. The basic trend is we gotta, so future generations will thank you for your honesty here. We'll be a little more careful with Project 3. All right. Okay, so hide. Sure. Oh, I don't want to. Oh, sorry. Did I lose all that? Okay, good. All right. Here, I'll say cancel. All right. All right, good. So let's move on to the next topic, and we'll finish this next class as well. So remember, this is our high-level view of the computer. We spent a lot of time talking about the control and the data path. Okay, and we're not really done with those. But there's all this other stuff that goes on, which is how you talk to the computer, right? So a computer with no data in or out of it is not a very interesting computer. And a computer that has no way to interact with the outside world actually doesn't do much either. So, there's a general class of things that you have to interface with. And, here are some examples. So there are some devices that are, kind of purely input devices. So the keyboard and the mouse. Although even like on my cell phone, the keyboard is actually an output device as well because it buzzes when I do the wrong thing. There are things like displays and printers, okay, that are output devices. And again, when you start having, touch screen, now all of a sudden the display is also an input. So this is all changing. It's interesting. And then, there's places. So these are for dealing with people. And then, there's disk, which is where our data lives long term, and the network, which is where the rest of the world lives, okay? And those are both input and output. So what we want to talk about the rest of today and on Wednesday is kind of how this stuff talks to this stuff. That's really what we're going to spend time on. So, why do we care about input-output? It's what we just said. That's how you interact with the computer. That's where the long-term memory is. And then this is a picture of the original Sixth Sense. And you can see it here. It's, something that you could only wear at MIT. But, you basically have a camera and a little projector that you wear. And it recognizes hand gestures. It's really very cool. There's the trick of typing a phone number on your hand. If for some reason you think projecting a watch on your wrist is better than wearing a watch, you can do that. And if you're a Harry Potter fan, you can watch newspapers that have moving pictures. So it's cool stuff. And, I don't know if this is your quote, Dan, but basically a computer without I.O. isn't worth anything. And you can come up with your own analogy. That'll be for next time. One of the challenges of I.O., there's really two big challenges. One of the big ones is sort of this huge disparity in speed, okay? And part of it depends on whether you're dealing with people or other machines, okay? So people tend to be a little slower than machines in general. and for certain things, not for others. There's basically 7 orders of magnitude here from a keyboard, which is basically like 0.01 kilobytes a second, to a gigabit switch, which is 125,000 kilobytes per second. Okay, so that's a huge disparity. That remember, what we're trying to do is get this stuff to talk to our processor. Our processor, of course, is running at gigahertz, and then we've got all this stuff that's running at these very, very different speeds. Right, 7 orders of magnitude is a lot of orders of magnitude. Okay, the other problem with the I/O devices is that the processor doesn't directly control them. Okay, if your I/O device is a mouse, your processor, I did this. Hey, my processor was minding its own business, enjoying the lecture like you guys, and then I go and touch the mouse, and all of a sudden has to wake up and start doing stuff. So you have this asynchrony that you have to deal with as well. So those are really the 2 challenges with I/O. Okay, so what do you need to make it work? Well, you need these 3 things. You need a way to connect lots of different kinds of devices, whether they're cameras or keyboards or disks or networks or whatever these things are. You need a way to sort of talk to them, right? Control them and move data back and forth. And then you need a way for programs to be able to access them, right? So if you're trying to write a program that reads input from the keyboard, that has to be done in a way that makes sense, to you as a programmer, right? And if you've ever written any, UI code, it's actually pretty tricky, right? Because you've got to be able to deal with a mouse interrupt at any time or keystroke at any time and so on. Okay, so, but you need the right abstraction so that the programmer can deal with the input and the output as well. Okay, so input and output's a pretty wide topic. It includes really slow things like, mouse clicks, and it includes really fast things like, streaming megabytes of data off of a hard drive. Okay, so, so how do we do that? How do we make that connection? So, one way to do it is by having special instructions, okay? And again, this will be at the assembly language level. So you can have separate input and output instructions. So you can have an input, which is going to read a sequence of bytes. You can have an output that writes a sequence of bytes, okay? And some processors do have special instructions for this. But the MIPS actually doesn't. The MIPS uses another technique, which is kind of interesting. It's called memory mapped input-output. And what that does is it basically just uses loads and stores to handle the input and the output. It's kind of interesting. And the way it does that is it has a special portion of the address space that's set aside for communication paths. Okay? So if you do a load to one of these special addresses, a load from one of these special addresses, you're actually reading from some sort of a device. And if you do a store to these addresses, you're actually writing to the I/O device. Okay, the hardware is going to do that, play that little trick under the covers for you. Okay, so here's the way it could work. So here's our memory. It goes, from 0 up to 4 gigabytes. And we have these special addresses starting at FFFF0000, which are where we're going to do our memory mapped I/O. And these actually are going to correspond to sets of 2 registers. Okay, and we're going to have a set of registers for every device we interface with. And those registers have 2 things. One is the control register, which I'll show you in a second. And that's just going to say whether the device is busy or not. And the other is a data register, which is where the bytes actually are. Okay, so if you want to write or say read 4 bytes in from some device, you would go to the right location in memory for that device, and you'd say load word. Okay, and if everything works properly, you'll get 4 bytes from that device. Okay, so there's a couple problems here. Well, I already mentioned some of the problems, but another problem is this processor I/O speed mismatch. And remember, processors run really, really, really fast. So if you had a machine that could do 1 billion load or store instructions a second, okay, then, if let's see, execute 1 billion load or store instructions per second, so that's 4 million, had to get my orders of magnitude straight. So that, so if you're doing that 4 bytes at a time, that's 4 million kilobytes a second, okay, which is really fast. That's faster than our fastest I/O devices. So, as we said, our fastest I/O devices that we're thinking about were gigabit links, and that's 125K bytes. Maybe now you have 10 gigabit links, so it's a factor of 10 more than that. But it's still way off of 4 million kilobytes a second. So the input device might not be ready because it's slow relative to the processor. And the output device, same thing. Okay? So you've got the processor that's potentially able to chew through all this data. The devices run at their own speeds, and you have to match those. So what do? Well, we're going to come up with two ways of dealing with this. We'll talk about the first one today, and we'll talk about the other one on Wednesday. So the first one is basically to have the processor check that everything's okay before it does anything. And this is where we're going to use that control register and data register. So the control register is really just going to be a bit that says, is the device ready or not? Okay? And then we'll use the data register, as I said, to pass some number of bytes, either from the I/O device to the processor or back. Okay? So what's going to happen is, in this scheme, this is called polling, the processor is going to keep reading the control register. Okay? And it's going to treat what's in that control register as a ready bit. And if that bit's set to 0, right, it's deasserted, that means the device isn't ready. So the processor just keeps looking at that register until it sees that it's a 1. When it sees it's 1, that means the device is ready, and then it can do what it needs to do for the data. Okay? So if the ready bit is set to 1, then the processor, if it's doing a load, reads what's in the data register. If it's doing a write or a store, then it writes to that data register. Okay? And then it's up to the hardware to make sure that the transfer happens correctly. Okay, and this is called polling. So, what does this look like in code? Well, basically, here's where we start our special region of memory, right? Remember, it's called memory mapped I/O. So let's say that our keyboard is the first set of registers. Okay? So we're going to load our special address. Okay? And then we're going to check. We're going to keep going. We're going to keep looping, right? This is called busy waiting or spinning. We're going to keep looping until we find that control register is set to 1, which means the device is ready. And then when it is, we actually load the word from the next 4 bytes, which is our data register. Okay? So the control register is 4 bytes. We then read the next 4 bytes, which is our data. So if you wanted to read 4 bytes from the keyboard, that's how you do it. You check the keyboard's ready bit until it says it's ready, and then you look in the data register, and there's 4 bytes for you, okay, coming from the keyboard. That's how you get stuff from the keyboard. If you wanted to write out to something, say the display, well, the display is a different device, okay, so you can't use the same address. So there's a different set of registers for the display. So again, we load the base of the I/O memory region, and then we look at the control bit, the next ready bit, which is in the next control, which is in the control register, which is 8 bytes after our first register, right? So because we had 4 here for control, 4 for data, and then the next 4 bytes will be the control register for our next device, which in this case is the display. Again, we loop until the device is ready, and when it is, then we can write out to the display, and here we're going to write to the data register, which is, of course, 12 bytes from the start of this region. Okay? So that's it. So basically, the ready bit is just there, and this is called polling. Now, what's nice about polling is it's simple. You don't even need any new instructions, right? This is just good old MIPS instructions, and all of a sudden, we're doing I/O, right? Because the hardware is going to play it made this little agreement with us that these special memory regions would be registers for I/O devices. Okay, and of course we have to agree on which pair of registers goes to which device. Okay? But what's the problem with this approach? Or what's a problem with this approach? Yeah, in the back.
Just using an input doesn't do anything for the program. It's not aware of when something is exactly.
Yeah, I mean, the problem here is that because you don't know when something, remember, I/O devices are external to us. Okay, so we don't really know when they're ready. So in this scheme, we can't do anything but keep checking. And remember, look how we check. We're actually running instructions. So, we're blazing through instructions, right? We're getting TLB hits all over the place, right? But it doesn't matter because they're not doing anything. They're just spinning, waiting for that bit to go from 0 to 1. Okay, so the problem with busy waiting or spinning is that you can spend a lot of time polling. Okay, so how long does it take? So let's say on average it takes, say, 400 clock cycles to call the polling routine, to access the device, and then get the answer back. Okay, so what's the percentage of time you spend polling? Okay, well, the answer is it totally depends. If you have a mouse, typically you'll pull a mouse like 30 times a second, right? Because you don't want to miss, if somebody's moving the mouse, you don't want to miss that. But you don't have to do it like every nanosecond, right? 30 times a second, you'll get pretty good resolution on somebody moving a mouse. So 30 times a second, you'll pull for mouse. There used to be these things called floppy disks that were in the notes, so sure I left it in there. And basically those were storage devices. You guys probably don't remember. But they weren't very powerful. They didn't store a lot of stuff. And you could move data sort of 2 bytes at a time, back and forth. Okay. And so they had a data rate of about 50 kilobytes a second. Okay. But you can't miss anything, right? Remember, if this disk is giving you a page at 2 bytes a time, you got to be there for the processor has to be there to pick up every 2 bytes. Otherwise, it's going to lose data. Okay? So you got to be there. And then hard disks are going to run quite a bit faster, say 16 megabytes a second. And in this scheme, they're going to transfer 16 bytes at a time. Right? Because remember, these data registers can be different sizes. So that the example we looked at, the data registers were 4 bytes. But, they could be 2 bytes. Well, maybe not 2 bytes, but in this case. But, 4 bytes, it could be 16 bytes. It could be a little bigger than that. Okay? So, very different impact of polling. So for mice, where you're only looking 30 times a second, if you do the math, 40 clocks per poll, so 12K clocks per second, that's nothing. That's peanuts. So you can easily poll for the mouse, okay? And you're only using that much of your processor speed. That's not a problem. Okay, I removed the floppy in there, but the floppy you could actually poll to. The problem is, when you try to poll for the hard disk, that's a problem, because remember, it's giving you 16 bytes a chunk, and you can't miss one. So you've got to be there, just poll. And that, if you work out the arithmetic, could chew up a huge amount of your CPU, like 40% in this case. Okay? So there's really two. So the point of this is that polling is perfectly fine. It makes perfect sense, and MIPS supports it with the code that I showed you. And for something like a mouse that only happens, a few times a second, and polling's the way to do it for sure. Okay? For something like a hard drive, which is going to send you a bunch of bytes in a big stream, polling's not a good way to do it. We'll talk about next time another way to do it, but actually we're going to want to do something different for disks and for mice. Okay, so let me just, I've got one last slide after this. So what we're going to do, so polling, as you said in the back, has this issue that it's constantly looking. The alternative is to use an interrupt. Just hold on just a second, I'm really almost done. Use what's called an interrupt, where the processor goes off and does something else, and it says, hey, I/O device, wake me up when you're ready. Okay, and that's what an interrupt is, and that's what we'll talk about next time. So in conclusion, our topic for next time is I/O, why it's important. We talked about polling. We'll talk about interrupts next time. And that is it. And then we'll have Thanksgiving.